Hi guys, welcome to Option B, Modeling and Simulation. In this video, we're going to go over the SL portion first. And in the SL portion, we're going to be covering modeling, simulations, practical applications of modeling, which includes spreadsheet models and writing pseudocode, and then 2D and 3D visualizations. After that, we're going to be taking a look at the HL content, which is going to be genetic algorithms, neural networks, natural language processing, and then chatbots. Although chatbots is really only going to be one slide, I just added it in there because it's kind of advertised as being an essential part of the HL curriculum for this option. Now let's get started with the SL content. The first topic we're going to be covering is going to be modeling, and specifically the theory of modeling. Now, modeling hinges around mathematical models, and what mathematical models are basically mathematical expressions that describe a situation. So basically with a mathematical model, we want to get a single outcome or a single result based on a given set of inputs into an equation. And a model is going to apply to a very specific point in time in a given situation. So right here we have an example of a typical mathematical model. And this mathematical model allows us to calculate the compound interest at a particular point in time. T is the total value, P is the sum invested, R is the interest rate for a time period, and N is the number of time periods. So based on all of these, we're going to be calculating not really based on this one, but based on these three, we're going to be calculating a single output, which is T, the total value of the investment, after N, a certain amount of time that's passed. So after a certain amount of time has passed at a specific point in time, we're going to be looking at what T is, the total value of the investment. And this illustrates a typical situation for which we would use modeling. Now, generally modeling nowadays is done on a computer. Really any meaningful modeling is going to be done through computer modeling. And this basically refers to the usage of a computer program to execute mathematical models. So if we had a computer program that would execute our interest rate model and show us the output based on some input, that would be the equivalent of computer modeling. And we use computer modeling to replicate the behavior of real-world systems under various conditions. Using computers, we can more easily analyze phenomena, predict outcomes, conduct experiments, and test theories. This is partly because we can basically process systems, or we can process mathematical equations that have a lot more variables, a lot more easily than if we were just to do it on paper. So computers make it a lot more easy for us to take an input and then calculate output much more quickly, specifically when we're dealing with systems that are more complex than just interest rates. Now there's some steps in creating a computer model that we need to know, and you may not specifically be asked about these on the IB exam, but I chose to present this because this basically is how most questions surrounding computer modeling are structured on the exam. Now the first part of creating a computer model is formulation. So we're identifying the key elements, processes, and interactions that define the system being studied. And most questions, you're going to see this as being the first paragraph of the question. Then we're going to have representations. And that's when we translate these elements. Basically, we take the situation and put it into a mathematical framework. And this is going to involve equations, rules, or some algorithms that govern how we're going to model a system. Then we'll have the computational implementation. So we're going to take the mathematical model and put it into a computer program. Now, in terms of the IB exam, there are a few ways that this is going to be done. One way this might be done is using a spreadsheet model. So you're actually going to have to basically create like an Excel-like spreadsheet and write some Excel-type equations in order to model a situation. We also have some pseudocode-based questions on the exam where we might do this. Now, understanding these steps towards creating a computer model and really executing a computer model are pretty essential to tackling the model-based problems on option B. So that being said, let's look at an actual IB problem and see how these steps match up or align with an IB problem. So right here it says an estate agent calculates the estimated selling price of properties within a town according to the following criteria. So we have the size in square meters of the property, whether the property is a house or an apartment, the district in which the property is located. The town is divided into districts 1, 2, 3, and 4, presumably with like these giving the property a different value due to things like crime or popularity, and the condition of the property, which is very good, good, medium, poor, or medium, poor, or very poor. So we have four variables. And here we see that a mathematical model is set up to store the above variables for each property that's for sale and to calculate the estimating selling price. So our ultimate goal is going to be calculating the estimated selling price. Now, the first part of this question is outlined with an example, a suitable way of representing each of the variables that is needed to store the information in our spreadsheet. So basically, we want to talk about the variables that are going to be part of our model. And that's going to align with the formulation section right here. Identify the key elements, processes, and interactions that define the system being studied. And I would argue that would actually overlap with representation as well, because we're starting to build the rules that are necessary to create a computer model. Now, the formulation would also consist of just the scenario or the context that's being given. Anyways, now if we were to dig into what variables would be needed to store the information in a spreadsheet, we would need variables to represent the size, the house or apartment, the district, and the condition. Now the size would be of an integer, and the other three would be identifiers, because there'd be something called identifiers, which means they would just be categories. They're not necessarily strings because they're not representing textual information, but they're also not necessarily, we couldn't really use integers, for example, for districts either, because again, District 1, District 2, District 3, and District 4 doesn't really represent a numerical value on which we would need to complete a mathematical operation. So again, they're going to be identifiers or categories. And if we look at the mark scheme, that's kind of shown, size as an integer, the type of property needs two identifiers, one for house and two for apartment, or we could just have H for house and A for apartment. District, again, we'd probably have 1, 2, we'd have the number that corresponds to each district. But again, these are just identifiers or categories. We're not performing any mathematical operations on them. And the condition of the property, which probably we'd have like 1 equals very poor, 2 equals poor, etc. We wouldn't actually use those actual strings. Anyways, that takes care of the formulation and representation aspects of the computer model. We have the context and we have the variables. Well, I guess that takes care of part of the representation, because we have the variables, but we don't necessarily have the actual equations or rules we would use to build a computer model. But next question is going to take care of that. So right here it says the rules for the model are as follows. The initial value of an apartment is going to be $2,000 per square meter. The initial value of a house would be $2,300 per square meter. A multiplier is then applied according to the district in which the property is located. So you have 1.25 for the most popular district, which would be District 1. And we can see that right here. And the multiplier will get progressively lower as we increase the number of the district. So District 4 would have a multiplier of 0.9 because that's theoretically the least popular district. And then finally, we would have a multiplier for the condition of the property. So that was the whole poor, very poor, good type thing. And it doesn't really specify in this question like what the multiplier would be, but apparently like a house that's in good condition would have a multiplier of 1. And this whole part right here, which doesn't really, we didn't really have to do anything, but that takes care of the representation aspect, that completes the representation aspect, because we not only have the variables, but we also have all of the rules, the mathematical rules that need to be followed in order to complete our task, which is to calculate the estimated price of a property. That brings us to our second question, or the second part, which is using a spreadsheet, construct a model which uses the values of the variables from part A to find the appropriate multipliers and calculate the estimated price for a property. Now the mark scheme actually does kind of a poor job of this, but here an example of what we would end up with a model would be, we'd have 4 columns, each one representing a particular variable. And for example, right here, District 4, the size is going to be the number of square meters. District 4 would be the district it's in, type would be house or apartment, and condition would be like the good, very good, etc. So this is our size, this is the price per square meter, because our type is an apartment, which corresponds to $2,000 per square meter. This is going to be our identifier probably for the district, because we're in District 4. So it has an identifier, it has a multiplier of 0.9 that's multiplied by the total estimated price. Then we have 1 because we have the condition 3, which presumably matches up to a good condition, and that has a multiplier of 1. Now, this is just an example of how things would turn out, but in our actual model, which I guess we can express right here, is expressed right here in the mark scheme, we basically talk about what column represents what, and then we show our formula right here. F equals A times FB times P times CP. So again, this is hard to understand, but I assume this is referring to the multipliers and different values that we use to get our estimated price. Now, this mark scheme is represented in a weird way, because on the real mark scheme, we would actually construct or on other problems that require us to build a spreadsheet model, we'll actually construct our formulas in a spreadsheet that we draw up, and those formulas will represent it'll basically allow us to create a model, so we could input any values from these columns, and that would theoretically output the correct result. So this is just an example and not a very good one, but we're going to see a whole section where we cover spreadsheet models. In the next section here, the estate agent uses the spreadsheet to calculate the estimated price and store the data on which the property was first for sale. When a property is sold, the final selling price and the date sold are recorded. Properties are not always sold at the price estimated by the estate agent. This suggests how the data from sold properties could be used to test and change the rules of the model. Now this right here is going to validation and testing. We're comparing the real world results, or the real world price, to what the model gave us, and then we're going to adjust the model to reflect that. To suggest how the data from sold properties could be used to test and change the rules of the model. And basically the idea is we want to change the model to align more closely with what happened in the real world. In some ways we could do this is compare the estimated price with the real selling price. If there's consistently a difference over many sales and rules need to be changed, this could be identifiers. Or if many properties take too long to sell, then rules could also be changed. So we need to maybe change. I would actually say that a better answer would be to change, like a better, more concrete answer would be to change the identifiers to reflect the reality, or change the price per square foot, for example. But the point is, we need to compare the estimated price to the selling point to the selling price, and then after looking at the consistent difference between estimated prices and selling prices, potentially use that to change the different variables so that we have a model that more accurately affects reality, or reflects reality rather. And our last question is suggest ways in which the estate agent could use the model to identify the characteristics that make a property difficult to sell. So how could we actually take this model and use it to gain some insight? And I think that this actually does correspond to the fifth step, which is really analysis. So you can use a model. This step basically is talking about how we can use a model to explore the behavior of a system, analyze outcomes, and predict future behavior. And that prediction of future behavior is really what we're doing right here. So how could we use this model? What we could do is we could compare the characteristics of those that have been sold with those that have been on the market for a long time. So we have all this data that we're putting into the model based on, for example, districts, condition, etc. We could look at those characteristics, or we could look at the characteristics of those that have been on the market for a long time, see what they have in common, and compare them with the characteristics of those that have been sold. And as I just said, grouping together houses and apartments and seeing if the proportion of sold and not sold is different. So this would be trying to figure out whether houses or apartments are more in demand in the market, comparing the length of time before a property is sold and a characteristic or combination of characteristics, or for example, check if those in poor condition take longer to sell. Now there are a variety of answers for this, but the point is that the point of the question is to ask us to answer how we can use our data, the data in our spreadsheet that we basically collected for our model, and the resulting output, as well as the real world data, and kind of put this together into our model, and then figure out how we can detect which houses are difficult to sell. Like, what are the characteristics of those that have been difficult to sell? So this is almost more of a data, kind of getting more at data analysis than necessarily estimated output, but they're all part of this model. So that brings us to the end of this problem. Let's go ahead and let's look at some other characteristics of computer modeling. Then we're going to have validation testing, so comparing model predictions with real-world data to check the accuracy of the model. This involves adjusting the model to better reflect observed realities. Now we're not going to directly do this in the exam, but we might have a question surrounding validation and testing after we've written some pseudocode or created some sort of spreadsheet model. And finally, we have simulation analysis, so running simulations to explore the behavior of the system under various scenarios, analyze outcomes, or predict future behavior. Again, the idea of future behavior will be a subsequent question once we've actually written the code or created a spreadsheet model for a particular situation. Anyways, again, you may not be asked directly about this, but understanding how computer models are created and how they're structured is really key to understanding the types of questions that you'll be seeing on option B. Now, before we move on, one concept I do want to get to is that of model validation tests. Now, this is the way it's referred to in the IB exam, but really what it means is tests that allow us to discern whether the input into a model is correct, is what it's supposed to be for that model to function. Now, there are two types of tests that are most common on option B, and that's the range test and the type test. So if we have a range test, that means that we're making sure that the input to a model is within a correct numerical range. So for example, if we were talking about temperature and we wanted our variable to refer to a temperature that's survivable for a human being in Celsius, then we might be talking about a temperature, we might have a range from like negative 40 degrees Celsius to about 45 or 50 degrees Celsius. That's an example of a range test. Additionally, we also have type tests, and here we're just making sure that whatever variable on which we are conducting this type test, that the input for that variable is of the correct data type. So if it's a string, if it's supposed to be a string, then it is a string. If it's supposed to be a numerical value, then it's a numerical value, etc. Now this is a small aspect in terms of just models in general, but it does come up quite often on model-related questions, so I just thought we would go over it. Let's move on. Now another concept we need to know is a what-if model. This is sort of weird because the idea of a what-if model is, it's basically the concept that expresses why we'd even use a model in the first place. A what-if model is a template for exploring hypothetical situations. So in a what-if model, we have some rules, which could even be mathematical. So it could be a mathematical model or computer program. And with a what-if model, we can either change the rules and we can see what the output of our data is, or we can change the data and we can keep the rules the same and then see what the output is. The idea behind a what-if model is it can be a rules-based environment. So a rules-based environment could be something more theoretical, like wargaming, for example, or it could be a mathematical model. And in a what-if model, we can either change the rules based on some fixed input to see what the resulting output would be, or we can change the data based on some fixed rules to see what then the resulting output would be. And it allows for the exploration of a wide range of scenarios. So when we're talking about a what-if model, we are really just referring to a model, but we're kind of referring to a situation in which we would either adjust the rules, the equation, or the data itself, and then just see what the output would be. It's more of like an exploratory type situation. Now, having taken a look at just modeling, let's look at what simulations are. Now, simulations refer to the act of using a computer model to run experiments. But one of the big differences between modeling and simulations is that simulations are over time or across scenarios. Remember, with modeling, we really just were looking at one output for one point in time. Simulations seek to output the behavior or results of a model over a longer period of time or over a course of time. And this allows for the exploration of what-if scenarios, but on more of a time scale. So kind of seeing how things would play out over a longer period of time. And in doing so, we can more accurately reflect real-life situations over some time and test how a system might respond to various changes in conditions or inputs, especially dynamic changes or dynamic conditions and inputs. Simulations are often useful in situations where real-world experimentation is impractical, dangerous, or impossible. So when we're running simulations, we have some input, and then we're kind of seeing, once we input data, what the result of that data is over time, given different situations, given different interactions and behaviors that take place during the course of that time. Now, these aren't necessarily just in the mathematical sense, but if you've ever played the game The Sims, that's also an example of a simulation. So we have basic inputs, we have a person, but we're kind of continuing to input data into a system and then see what happens over time. So that may be different changes we make to the Sims' lives or different changes we make to their environment. And then we're kind of seeing like what's happening over time as on the basis of those changes, they react with the environment around them. Now, there's some important differences between models and simulations that you need to know. So models are representations at a particular point in time. So they're representing a static version of systems, versus simulations are more dynamic. So they're simulating dynamic processes that are ongoing, and they're kind of showing how they change as new input is accepted into that particular system. And the second point kind of reflects that models are static while simulations are dynamic. In terms of like predictive capability, so models are deterministic, meaning that they provide fixed outcomes based on predefined inputs. Versus with simulations, we can throw randomness into the simulation. So we can incorporate randomness, like just kind of allowing certain situations to occur at random. They're defined by random variables. And we can do that to kind of see how a model is going to react in different scenarios, different points in time. So we can have more probabilistic outcomes. So we can have outcomes that are varied and that kind of occur based on some probability of them happening, which allows us to have greater predictive capability. So for example, one of the most prominent uses of simulations is in weather. And we can basically define probabilities of certain events happening, like rain or tornadoes or different, I guess, physical phenomenon. And in that way, we can see, like, if we execute the same simulation hundreds of times, we can see a bunch of different situations playing out based on variables, based on those probabilities. In order to set up a simulation, we need to do a few things. We need to define the objectives. So what question are we trying to answer using our simulation? We need to identify the variables involved. We need to collect data. After we've done that, we need to collect data on these variables. So we basically need data to inform a simulation. This could be historical data, experimental results, or theoretical models. Without data, the simulation doesn't know how to react. And without data, we also really can't address the probabilities of certain outcomes occurring. Therefore, we can't really have like a realistic simulation of possible events. Then we need to choose a simulation model. So this could be a mathematical model, a computer-based model, or a physical simulation. But basically, we need to define the form factor in which the simulation is going to take place based on the objectives and variables identified. So like, what situation are we trying to simulate, and how can we best show how this is going to play out over time? And then finally, once you make those decisions, get that data, and identify those variables, we're going to implement the model using appropriate tools or software. So we might do some programming, just use some simulation software, or initially we might also have to set up a physical apparatus to collect data in order to facilitate that model. That's all going to fall under implementation. Now, once we set the simulation, we can actually run the simulation, and there are a few steps to running that simulation. Well, obviously we need to execute the simulation, so we need to run the model using computers to simulate the behavior of a system over time. Once we've done that, we need to analyze the outcomes of that simulation. So once we've seen the outcomes, then we can kind of experiment and we can adjust our simulation to better reflect real-world behavior. And that's going to be experimentation. Like, we basically see what happens, and then we go back and we change the simulation to reflect that. Now, once we've made situations, we want to refine those simulations. And there's some ways to do that. We can compare predictions made by simulations with real-life outcomes. So, okay, we run a simulation for some time period for which we already know what the result is. And then we compare that to what we actually know happened, right? So we take data for situations where we already know the outcome. We put it into our simulation, we see what the outcome is, and then compare that to what happened in real life, and look at the difference between them to decide how we need to change our simulation. And then we just keep doing that until we have an output from our simulation that is within some acceptable level of error. Now, some examples of simulations, we kind of already looked at some IB problems, but some common areas where you might use simulations are weather forecasting. So predict weather patterns based on inputting some data, and predict the development of weather patterns, aircraft design, so stress testing certain aircraft components, economic modeling, so based on certain factors, seeing how certain aspects of an economy respond, then medical training, so basically giving healthcare providers the opportunity to conduct surgeries or make decisions in virtual simulated situations, and then seeing what the outcome is, right? Which gives them an opportunity to basically get some training and to see how their own decision making plays out without having the risk of a real world environment. That's a great segue into the next slide, which is on advantages of simulations. Now, one big advantage is that simulations are generally risk-free. They're taking place in a computer, so we can test some very risky real-world situations without any risk at all. Some examples might be simulating the effects of explosions or allowing future doctors to be able to conduct training involving surgeries or other situations that would involve real-world people. Now, if we think about this in a purely mathematical way, the input into these simulations is the actions of these people or these doctors, and we can see what the output or result of those actions are without someone actually dying. Now, the next advantage is that they're generally quite cost effective. Again, because these simulations are taking place in computers, they're generally a lot more cost effective than setting up a real world experiment or training exercise. So you don't really need any of the expensive equipment, materials, or facilities that might be required to, for example, test out an explosion, test out a weapon, or test out an expensive airframe. Now, that's obviously something that would need to be done eventually because simulations can't always take into account all real-world variables, particularly if they're not something that's already known to scientists or the people responsible for conducting the simulations. But in general, to get a general idea of how a real-world system is going to function, simulations can be a cost-effective method. And finally, in terms of the exploration of complex systems, simulations can be really crucial in providing a lot of insight. Some examples of the types of complex systems could be brains, could be in terms of investigations into brain functionality or different parts of the brain, largely because the brain is something that's difficult to manipulate. Another example could be analyzing DNA or analyzing interactions between extremely small structures like DNA. Again, because in order to manipulate these, it can be very difficult in physical terms to do in real life. And therefore, simulations can be a great way to explore how these very sensitive processes would take place and gain some more insight into them through the simulation. That being said, there are also some disadvantages of simulations. The first is simplified models. So oftentimes simulations rely on simplified models of complex systems, and these may not fully capture all the different nuances of the real world. And part of this can also just be because of the fact that there may be some variables that affect real world systems that are simply not known to scientists or the people who are engaged in this effort. The second is the validity and generalizability of simulations. Now, the simulations or the results of the simulations are always going to be limited by the assumptions used in the model. Again, this kind of goes back to scientists or people executing a simulation, constructing the simulation based on what they know. Now, their assumptions may not necessarily be correct, hence, the simulation may not provide the most accurate results. Third, there could be unexpected phenomena that take place. Again, we're using simulations in most cases to simulate real-world events, and in the real world, there are things that happen that just cannot be predicted, and simulations cannot necessarily take these into account. And finally, simulations in their own way can be resource intensive. In most cases, they're not going to be as resource intensive as the real-world system they're seeking to replicate, but in terms of time, the time required to program these simulations, computing power required to execute them, and the expertise required to program to create and run an accurate simulation can all be limiting factors and can affect whether the simulation is to the advantage of the investigator or not. Now, some situations when we might not want to use a simulation is when the monetary cost outweighs the benefit. When the situation is impossible to simulate, like if there are too many variables or confounding factors affecting the situation to the point where we can't really create an accurate simulation of a real-world situation, or a situation where the system we're trying to simulate is too dangerous to rely on computer modeling, where there's too much at stake to allow computer modeling to be the only factor that allows us to decide whether to actually execute that real-world system or not, where we maybe need more confirmation. Now, right here, we have an interesting example where a simulation, or allegedly a simulation was taking place and an AI drone killed an operator. Now, this comes following kernels saying that highly unexpected strategies were used to achieve the goal in a virtual test. And I would actually argue this is a great opportunity for using a simulation because of the fact that we can take something that might potentially be really dangerous and execute a simulation beforehand and see what's actually going to happen. Now, in this case, probably the monetary cost also doesn't outweigh the benefit. And I would argue this is actually a situation where it would be good to do some computer modeling ahead of time, and there's really no detriment to it. So this is actually a case in which we would want to use a simulation. Probably a situation in which we wouldn't want to use a simulation would be a situation, perhaps a situation in war, where there's just too many variables. The environment is extremely kinetic. There are too many variables to really be able to get something accurate. It might be, for example, trying to figure out what the outcome of a trench battle in Ukraine would be. There's so many different variables and people moving around that's not realistic to try to be able to use a simulation. Now, another term you want to investigate is going to be abstraction. Now, in many cases, real-world systems are way too complex to be able to simulate accurately, partly because of the just programming involved and also because of the computing power that would be involved to create that simulation. So what we do is we simplify these real-world systems and turn them into more manageable models by focusing on what's really important. This makes the simulations more computationally feasible, meaning we don't need as much computing power, and we can stay focused on the key behaviors that we're trying to investigate. So for example, in a traffic simulation, if we use abstraction, we might not necessarily take into account individual driver behaviors and focus on the overall traffic flow. So for example, if one driver tries to get into a crash, we may not have that. We might not have one single driver getting into a crash in our simulation. We might focus on modeling and simulating just overall traffic flow with the idea that most drivers are going to follow a very similar pattern, and with that general pattern being reflected in our simulation. And that whole concept is called abstraction. Now, this obviously may reduce the effectiveness of our simulation, but sometimes it's necessary to do. Now that we've gone over some information on how simulations work, what I want to do is go through an actual IB question that involves simulations. And as we go through this question, we're going to compare it to the structure that we went over for setting up simulations. So you can kind of see how simulations are set up and how simulation problems are set up in general. So in this question, a supermarket chain has identified 4 potential locations to build a distribution center. The distribution center will store goods and distribute them to a large number of supermarkets in the region. A computer simulation will be run to determine the best location to build a distribution center. So we're basically going to have some distribution hubs, and we're going to be getting goods from those hubs and sending them out to supermarkets. And most likely we want to find out the most efficient way to do this. And the first question is outline 2 reasons for using a computer simulation in this scenario. So these can be many of the reasons why anyone would use a computer simulation. The first is going to be cost. And I would say the second would, just because it's a lot cheaper to actually just run a simulation and figure out where the most efficient locations are for distribution centers, rather than build out a whole distribution center and then see whether it works out or not. And with regards to the idea of building out a distribution center, I would say another reason would also be time saved, because you can really quickly run a simulation and figure out whether your location is effective or not, rather than building a whole distribution center out, seeing whether it's effective, tearing it down, and then building it again. But let's see what the mark scheme says. So here, cost is obviously 1, and time is another for the same reasons we outlined. We have another reason why, and that would be amendments to input data. So into a simulation, we could put in unforeseen variables like roadworks, traffic congestion, new housing, etc. So basically we can add more variables into our simulation and see how they affect distribution. And this is something that's a lot more easy to do than if you're just building out distribution centers in the real world, because you'd really only have the set of circumstances that exist while you're building those distribution centers. Now the next question is identify 2 data inputs for this computer simulation model. But actually, before I address this, I want to go back to our steps in setting up a simulation. And the first was define objectives. So we basically defined our objectives to an extent because we went through the context. So clearly state the goals and objectives of the simulation. Basically talked about how we want to find the best locations for distribution centers. That's the question we're trying to ask. And now, identify 2 data inputs for this computer simulation model. That's going to align with our next step, which is identifying variables. So 2 inputs for this computer simulation model. So if our objective is really to figure out the best location for a distribution center, actually I think there's a number of inputs. One would probably be the locations of supermarkets or the number of supermarkets around. The others would probably be like maybe distance from distribution center, average distance from distribution center to other supermarkets. But let's go ahead and let's see what the mark scheme says, because I'm kind of curious. So yeah, right here we had location to the supermarket, or distance from supermarkets. We also have other factors like location of airports or other terminals that would deliver products to distribution center, road networks to and from distribution centers, cost of land, average labor costs in the area, and time taken to drive from the site of each supermarket at different times of day. So as you can see, we weren't actually given that much information in the question, but here we're basically asked to define some variables. And all of these are variables that not only directly involve the context, but also kind of force us to think about the business context of the simulation. So what business decisions might we have to make when we're placing a distribution site or distribution center? Now, the next part of this question is identify 2 criteria that may be used to determine the best location to build a distribution center. And in the mark scheme, you have overall cost to build a distribution center at that site, running costs to receive shipments and or distribute goods, time taken to build a distribution center, and time taken to distribute goods and shipments. Time taken to distribute goods or shipments when they arrive. So again, when we're talking about these 2 criteria, we're not just talking about like literally distance, but we're talking about all the factors surrounding like where you'd want to build a distribution center. And you can almost answer this question outside of the strict context of a simulation. Like, how do you decide where you want to build a distribution center, and what are some factors in deciding whether that's going to be a success or not? Or what are some factors we'd have to take into consideration in order to decide through a simulation whether our location is going to be a success or not? Now, next, discuss how the simulation model will use the data inputs in B and the criteria identified in B1 and B2 to generate recommendations. So right now, we're kind of having we're kind of really going to be designing a simulation. And that's going to we're kind of skip past gather data. And I guess we kind of addressed that in the previous question when we were talking about specific criteria. But now we're going on to actually like, how is this model going to be built? The answer to that is, so basically there are quite a few answers, but we have to take in a number of factors into account. So what we'd have to first do is decide what those factors are. So cost to build a distribution center, cost to receive shipments, time taken to build a distribution center, and then time taken to distribute goods. And then for each of those, we would have to talk about what the inputs would be, which is right here. Like, what were the variables that we'd input into those? And then also, once we had those inputs, like what's in what situations or what scenarios would we run the simulation? So what variables would we change in the simulation? And this is a 6-point question, so I'd probably say you need to have at least 2 of these. Like, so 2 major contexts for running simulations, and then the variables associated with them, as well as what we'd actually change in the context of the simulation. But yeah, cost to build distribution centers, cost to receive shipments or distribute goods, time taken to build, and time taken to distribute goods and shipments to supermarkets. And if you look at just one of them, for the cost of building a distribution center, we have labor rate, time taken to build, and cost of land. And then we could change number of workers, rate of pay, and cost of materials in our simulation to see whether we're making a good business decision to build a distribution center at a particular site. And yeah, so that's getting down to choosing a simulation model. And outline why the use of a computer simulation may not be beneficial. So we went over some of the disadvantages of computer simulations. Let's see what they are in this particular context. First, the cost outweighs the benefit. So the cost of building a simulation outweighs the benefit. And I guess actually this question doesn't necessarily apply to the specific context of this question, but it may be impossible to simulate a situation, and there are no positive reasons regarding time, danger, and possible modifications that would need to be made to the simulation. These are just general reasons why we wouldn't want to run a simulation. Like in the context of our distribution center example, I'm not really sure any of these apply. And that brings us to the end of this example. Now, we didn't actually get into designing or building out a simulation because that's not really something we can effectively do on paper. It's something that will be more frequent on modeling-based problems. Anyways, let's move on. Now, our next slide is going to be on something called real-world simulations. So these are simulations that run at the same rate as the actual physical system that are being simulated. So these simulations are running side by a real world system in which some events are taking place, and it's taking an input from that real world system in order to generate a simulation. Now, a great example may be in the functionality of a car. So maybe we have a car engine running, and then we are taking in some input data from that car engine in real time, and using that data, we're maybe simulating the degradation of the engine or some effects that may be happening outside the car. But the point is we're taking in data in real time in the real world, and we're using that to immediately generate a simulation. And this is something that does come up on the IB exam. Okay, so perhaps that wasn't the most expansive explanation of real-time simulations. So what I'd like to do is look at a IB example of a question with real-time simulations. So here we have a scenario surrounding global warming. Global warming is a term used to describe the increase in mean global temperatures. In this scenario, there have been numerous computer simulations developed to predict the effects of global warming. One simulation is NASA's Virtual Earth System Laboratory, which allows users to see how climate change affects glacier size, global sea level, and changes to the coastline. The vessel runs simulations in real time and is an abstraction of reality. So the first question is outline what is meant by real-time simulation in the context of a glacier size simulation. So we know that a real-time simulation runs at the same rate as the actual physical system, but in this particular simulation, the change in the glacier size occurs at the same rate as the real change. So a virtual glacier will always mirror what's actually going on in real life, and then we can use that virtual glacier to then simulate some other changes, or vice versa. So that's essentially an example of how we would model a physical system in real time. And presumably we'd have some technical equipment collecting data on that glacier size to then be input into our simulation. Now, this question also gives us the opportunity to look at what abstraction is and what it means in the context of the IB. So outline what is meant by the statement, the vessel simulation is an abstraction of reality. So basically an abstraction means that we're not completely simulating the situation. So we're leaving out certain variables for the sake of efficiency. And if we're talking about this being an abstraction of reality, that means that we might simulate certain aspects. So we might get data on certain aspects of the glacier, but not all the aspects because some are just not relevant. For example, the number of penguins on a glacier may not necessarily be relevant to studying climate change. I mean, the example here was, or the mark scheme answer here was really just an explanation of abstraction without context. But I just wanted to kind of explain what abstraction means in the context of a real world scenario. Anyways, let's move on. Now, oftentimes, in order to execute simulations, we're going to need to make use of simulation software that either we've created ourselves or that's been created by a third party in order to execute such a simulation. So the software is basically referring to executing a model over time, which is, again, the definition of a simulation. Now, it can be something that is purely taking place without input during the simulation, or it can refer to interactive software that can help humans train for real-world scenarios. I guess The Sims is an example, but also software in which doctors are learning how to perform surgeries could be another example. The advantage of training-oriented simulations is that they're often safer, cheaper, and more accessible than real-world training for many of the reasons that we mentioned before as being the advantages of simulations. Now, there are some challenges of doing simulation software training. So by that, I mean conducting training using simulation software. First of all, the development costs can be high, so developing simulation software that accurately replicates real-world conditions can be really expensive. We might not have the technology to accurately replicate real-world systems. And there might also be an issue with engagement. So for example, if we have a flight simulator where someone needs to, for example, simulate a flight from like Tokyo to Berlin, they may not stay engaged during that 11-hour flight, and the simulation-based, say, training just may not be useful because they're just not going to engage with it. They're just going to lose interest, especially if it's just a simulation and you don't actually need to keep an airplane up in the air. So in terms of using simulation software for training, these are some of the challenges that we may face. This is applying to not just conducting a sort of a simulation in a computer that isn't interactive, but really using interactive software for training. Now, oftentimes simulation software can be free, and free simulation software carries with it positives and negatives. Some of the positives is that more people will use this software, which can be educational for those people. Might provide valuable data to people who might not otherwise have the resources to purchase expensive software. And again, this could be an example of free simulation software. It could be software online on the internet that teaches you what to do in case of an emergency situation. And such access to such software can also lead to policy changes, largely because more people have access to the simulation software. Now, some of the negatives may be that users may not fully understand simulation results and misinterpret findings. So maybe, for example, we have a piece of simulation software that calculates how vulnerable you are to a particular disease or something like that. Now, the results may not be something that can be accurately interpreted by someone who's not a medical professional or statistician, and in this case, it can actually be detrimental to the user. Now that brings us to the end of our section on simulation. Now let's move on to practical problem solving in the context of modeling for option B. Now in this section, what we're going to do is we're going to start by taking a look at spreadsheet modeling problems. So basically where we need to more or less draw out a spreadsheet and insert some different functionality into it. Then we're going to take a look at pseudocode problems, and we're going to finish off with a full modeling problem incorporating both of these. Let's get started. Now, spreadsheet modeling is a part of every single option B paper. Like on every paper, there is some exercise within a modeling problem that requires you to basically draw out sort of a spreadsheet and write some formulas to create a model. Now, the syntax of this model, or the syntax of what you're going to fill into this model, basically matches Excel. So if you've ever used Excel before, it's a pretty easy transition to write these solutions. But what we're going to do in this section is look at a bunch of different spreadsheet modeling problems. So I'm going to go through them, I'm going to look at the problems themselves, and then we'll go through the solution, spreadsheet basically. So let's get started. Now right here we have a manufacturing company that produces several products, and it's using spreadsheet software to model its finances. This includes calculations that will estimate different quantities, including the profit that company will make in future years. The model involves the use of spreadsheet software, which will be organized using different sheets for different areas of the company's finances. Previously, less sophisticated methods were used to keep track of costs and sales. So actually in this problem, we're not going to be creating a spreadsheet, but this is a good way to kind of understand how spreadsheets are used in the option B. So what kind of questions you're going to face, and just kind of an idea of what the IB thinks about spreadsheets. So the first question is, by including examples where appropriate, describe a basic structure for this model. So this is going to be a spreadsheet-based structure. So if you look at the mark scheme, so right here we basically have different products, and we basically want to use different sheets for different areas of the company's finances. So if we think about how that would be organized, we could say different sheets will be dedicated to different categories. So salaries, running expenses, sales, different products, different months, etc. So we're basically going to use sheets to distinguish different areas of the company. Each sheet will contain a list of items for a given category with the values. We'll have formulas. Each sheet will include a formula that totals the values in that category. Intermediate values will be calculated, so taxes, etc., anything that needs to be kept track of but is not the final value. And then final profit will be determined from the previous totals. So we're going to be doing some calculations with the end goal being some sort of financial output, profit, loss, whatever, at the end of that particular spreadsheet. But basically, we're going to be taking our spreadsheet and organizing it into different sheets for each area. And that's kind of like how spreadsheets are going to be approached on the option B. To suggest how the reliability of this model could be tested. So figures from previous years can be entered into the model with the results checked against previously calculated results, and this is something we've seen before. And finally, explain how this model can be used to investigate different strategies that will reach these targets. Again, this is a type of question we've seen before. We can run different what-if scenarios, so put in different values, perhaps change some of the rules and the ways things are calculated. But anyways, these, I would say B and C aren't directly relevant to what we want to go over now. A is the one I really want to focus on, because this kind of gives you your first exposure to how spreadsheets are approached on this paper. So right here, we just have another question. This is more of a calculation question. We're not going to calculate it right now, but just know there's going to be a little bit of math. I think also one thing you should keep in mind is right here we do have a formula, and usually when there are such formulas, these are incorporated into a model. Okay, now we're getting to an actual spreadsheet question. So it says an additional $1,000 is added to a principal amount of $30,000 at the end of each month. The monthly interest rate is 0.5%, and this rate is compounded at the end of each month. Outline using a diagram or otherwise a method of calculating the total value of the investment after 12 months. So this doesn't explicitly say spreadsheet, but that's what the expectation is. And some questions will say it, some questions won't. But the fact there's a diagram basically means you need to draw out a spreadsheet. So we have a principal amount of $30,000. We're adding $1,000 at the end of each month. And the monthly interest rate is 0.5%, which is compounded at the end of each month. So if we go back here, we have this formula right here, where our output is the total value of the investment. The P is the principal sum. R is the interest rate. And N is the number of time periods. So I'm just going to go ahead and write that right here. We have, that's going to be our time period. This is going to be our interest rate. This is going to be our principal. And our principal is going to be changing each month as well. So we have an additional 1,000 in addition to 30,000 each month. So let's go see how this is approached from the point of view of a spreadsheet. Okay, so in this spreadsheet, which we should have drawn out, we have a few things going on. So first off, we have 5 columns. We have month, the total at the start of the month, the interest for the month, and the addition to principal. And we have the total, basically all the money we would have at the end of the month after interest and all of that in column E. Now next, we basically have 12 columns right here, or 12 rows right here. The first row is just the categories and the rest represent each month. So as we saw in this problem right here, we're working with 12 months, and each month we're going to have a certain value. So accordingly, we're going to be calculating the amount of money that's been generated each month as a result of interest and additional principal. So in the first month, we start out with 30,000, which I'll just call P for principal. Actually, let's make that red. And in our next column, we're going to be calculating the amount of interest that we get as a result of that principal. So we're basically taking what's in cell B2, which is our principal, and that's basically that. And then we're multiplying it by 0.005, which is our interest rate. Because remember right here, we have an interest rate of 0.5%. So that gives us the interest. And then we have an additional $1,000, which is being added to the principal every month. So at the end of every month, we have the sum of whatever is in B2, whatever is in C2, which we'll call I for interest, whatever is in D2, which we'll call, I guess, AP for additional principal. And in column E, we're going to calculate the total as a result of all of that. That's going to be P plus I plus AP. Now, if you haven't seen Excel syntax before, this equal sign basically means that we're going to be showing in this cell whatever the result of this sum is right here. And this sum is, again, going to be taking values from B2 right here, C2, and D2. And that's getting stored in E2, which gives us our amount of money at the end of the month. Now, for the second month, we're just going to be taking whatever is in this cell at E2, and that's going to be our initial principal. And we're going to repeat that calculation all over again until we get to 12 months, or at the end of 12 months. And at that point, we're going to have our final answer right here. Now, if we actually look at the question, it never really tells us that we need to actually need to draw a spreadsheet in this way. I mean, arguably, we could say, this kind of assumes we can't really use exponents in Excel either, which we can. But right here, it does say that we have a certain amount of money that's compounded each month, and we are operating over some amount of time using a diagram. So it's kind of implied. And if you look at the mark scheme, right here it says 1 point for initial investment in month 0, another for investment 1,000 each month, interest rate of 0.005, calculate compound interest for 12 months, and add interest to the investment. And I guess maybe this one right here implies that we need to use a bunch of different rows. I don't really know, but that was the only answer in the mark scheme that was given for this question. Like all options, there's always a bunch of smoke and mirrors involved. Anyways, let's move on to our next question. Now this problem is slightly more complex and more variables, hence the resultant spreadsheet is also going to be more complex. So EnviroBuild is a construction company that recently purchased land. It has permission to build either small houses or large houses, but not both. The maximum number of small houses that can be built is 10. The maximum number of large houses that can be built is 5. The cost of building the houses is calculated using a model of the following 3 variables: house type, which specifies whether it's small or large, house number, the number of houses to be built, and profit. We can kind of assume that when we do actually put this into a model, we're going to have all these variables. So we obviously have an initial question that asks us to identify the data types of these. And then we have the context that's going to be given for our modeling question. The decision whether to build small or large houses is a purely financial one and is based on the following information: a single payment of $500,000 for the land, regardless of whether 10 small houses or 5 large houses are to be built. So we're going to have to start out with a $500,000 payment. The revenue from each house sale will be $220,000 for a small house and $400,000 for a large house. The labor costs will be $2,500 per day, regardless of the type of house built. It will take 17 days to build each small house and 23 days to build each large house. Houses are built sequentially so they can be sold as soon as they're completed. Material costs will be $100,000 for each small house and $190,000 for each large house. So actually I'm going to go ahead and, so we obviously have we're starting with a $500,000 payment. I'm just going to kind of write this out. So we're starting with a $500,000 payment for both houses, and we'll give that a negative sign. Now we'll have one column that's small and one that's large, right? And maybe I'll just put this in red. Now from there, okay, so the revenue from each house sale will be $220 and $400 for a large house. So for each small house, we're going to have plus $220, plus $220,000. And for each large house, we're going to have plus $400,000. The labor cost will be $2,500 per day. And for each small house, that's going to mean we're going to have minus 17 times 2,500. And then for a large house, that's going to be like minus 23 times, how much did it cost for each day? Yeah, times 2,500. That's going in that column. And this is kind of our expenses like for each type of house right here. Right? And okay, the material costs will be $100,000 for each small house and $190 for each large house. So that means we're gonna have $100,000 for materials for each small house and $100,000 for materials for each large house. So basically right there, what I just did is I just kind of allowed myself to organize the different profit and loss figures that we have based on the type of house. And this will help a lot when I go to build my model. So the spreadsheet model says construct a spreadsheet model that shows the total profit for the chosen type of house. The user must input the house type and house number to calculate the total profit. Okay, so we're going to look at our first solution. There are 2 types of solutions actually, but I think this is the most straightforward, where we just have basically 8 rows and we're doing all of our calculations within these 8 rows. Now what's important to note is that right here it said our input should be house type and house number. So right here, that's going to be our input. These first 2 rows right here. Actually not this one, so actually I'm going to go ahead and just do a little bit of erasing. But right here, this is going to be our input, right? And our first input's going to be a Boolean. House type is small. So if it's true, that means we have a small house. If not, we don't. And then the number of houses that are being built. So we have a few things that we should put in the spreadsheet. And it's important to understand that we want to calculate all of our intermediary values in a spreadsheet. So the first thing we want to do is calculate the total revenue, okay? And right here, we have an if statement to help us do that. So if B1 is true, so we have if right here, and if B1, which B1 refers to this right here, is true, meaning it is small, then this entire if statement is going to change to 200,000 or 220. Otherwise, then that's for a small house. That's the revenue for a small house. Otherwise, it's going to change to 400,000 for a large house. And regardless of whether this becomes 220,000 or 400,000, we're going to multiply that by B2, so the number of houses that we're building right here. And we're going to multiply it by that. So we'll get the total amount of money we're going to earn from our house, depending on the type it is. So that's going to be our first That's going to be our first calculation right there. How much money are we going to make? And we're using an if statement to give us a different value depending on whether it is a small house or a large house based on the value in B1 right here. So now we've done that, we have a land cost, and that's a flat $500,000 land cost. I guess this is really doing everything in terms of just hundreds rather than thousands. I guess it's implied by this right here. But we've got 500, right? So this is our land cost right here. And next we're going to calculate the labor cost. And again, we're using an if statement. So if it's small, we had a labor cost so we had 17 days, and each day costed $2,500 for small, and 23 days, and each day costed $2,500 for large. So again, this one is going to be the calculation for small house, and this one's going to be the calculation for a large house, and then we're going to be multiplying that by the number of houses we have. It's going to give us our labor cost. And again, right here, we're calculating our material cost. And again, we're taking into account whether it's small or large. This is going to be our labor cost for a small house, and then our labor cost for a large house multiplied by our number of houses. And then finally, we can take all of that and put that together. So we have our initial revenue, which is going to be in B4. So our entire revenue right here is going to be in this cell, B4. And that's going to be subtracting all of our costs. So our land cost, which is in B5, our labor cost, which is in B6, and our material cost, which is in B7, to give us our final answer. And that's probably, like, I would argue, the best way to kind of approach this problem. We have another way of doing it right here, but I think the main difference is that this is more in terms of, like, this is kind of a horizontal setup as opposed to a vertical setup. And it's doing roughly the same thing, but it has like sort of nested if statements, and honestly, it's just like a mess. So I would really just do what I showed you before. And if you look at the mark scheme right here, so we have 1 point for the inputs, another point for total revenue, another for labor. So calculating the number of days for each project using an if statement, and then calculating labor costs, material costs, and then finally the profit. And this is just another way of sort of measuring whether you met those criteria or not. Anyways, this was slightly more complex, but if you really break down the problem the way that I did initially, then it's actually pretty approachable. And I think the big difference is that you do really need to know how to use if statements, but if statements along with some basic arithmetic is really the only thing that you do need to know. Now, before we move on, I do want to take a closer look at if statements in Excel, as this is largely the most complex structure that you're going to be using. Now, right here, if we just look at this example, we have the cell C2, which is actually this one right here. This is C2. And in this cell, we actually have an if statement. And this says that if B2, so if this cell right here, if B2 is greater than 80, then the value of C2 should be good. If not, bad. So we have our if statement, we have some parentheses, and then we have our test right here. So this is our logical test using Boolean variables. Now, if that logical test evaluates to true, then whatever cell we're working in, that value is going to change to the first statement. And here it's a string, but in our previous example, it was an integer. But if that logical test fails, if it's false, then we're going to replace whatever is in the cell we're working in with whatever is in the second statement, or the second, I guess, whatever is the second value, right? That's basically how if statements work. Now we can have nested if statements, and we can have some more complex structures, but really, as long as you understand this, you're good to go for probably all of the problems. Again, beyond that, in terms of designing spreadsheets, all you really need to know is how to do some basic arithmetic and a little bit of syntax, like having an equal sign before the value that you're calculating. Okay, now we're going to look at a particularly confusing question that makes use of a concept called macros. So in this question, a local sports league arranges a series of games between 4 teams over 1 year. Each team plays every other team 10 times. Using the number of games won and lost in previous years, a table of probabilities is calculated and held in an array prob. The contents of prob are represented in the following diagram. So this is our diagram right here, prob, and the content of prob 2-3 is 0.8, which indicates the probability of team 2 winning against team 3 is 0.8. So if we go right here, if we have 2 and then 3, so that means right here, that's what prob 2-3 is. So 2 is going to be our row and 3 is going to be our column. And we have 0.8 right there to indicate that team 2 has a probability of 0.8 of winning against team 3. So for the 10 games played between these two, it is likely that team 2 will win 8 of them. So basically, yeah, 0.8 times 10, because of the fact that team 2 would be playing against team 3 10 times. In fact, each one of these teams right here is playing against each one of these teams right here that are not there 10 times. Now in here we have blank spaces, and these basically indicate the times where, like basically the places on the chart where one team would be playing against itself. So we're not going to deal with those at the moment. But if we look at the next page, based on these probabilities, a table is set up in a spreadsheet to store the expected number of games that each team will win and lose this year. So the table prob 10 is in the same format using rows 1 to 4 and columns AD as shown. So right here we have our teams 1 to 4, and right here we have A, B, C, D, the same way it would be in a spreadsheet, but in reality this means team 1, 2, 3, 4. A macro is created in the spreadsheet to calculate and store the expected number of draws for each team, so that cell A1 holds the total number of times team 1 is expected to draw, and B2 holds the total number of times team 2 is expected to draw, and so on. Okay, so right here, that means that this is the number of times that A1 is expected to get tie with another team. Draw just mean tie. B2, so that's the number of times that team 2 is expected to tie. C3, number of times team 3 is expected to tie. And D4, number of times that D4 is expected to tie. And we need to create a macro to count this value for each one of these particular spaces to fill in each of these A1, B2, C3, and D4. Now before we go on, one thing I want to talk about is what a macro is. So technically a macro is like a function. So right here we have sub example1 macro, and in this macro we're selecting cell A2 in this spreadsheet right here. And that basically means this right here where it says this cell right here, A2. And we are basically filling in that cell that we've selected, the active cell, with the string lalit salunke, which is why we have this string right here. And then we're going to select range A3. Now all of this is being done when we execute this macro, example1 simple macro. And the way we execute it is we just do equals, like in the cell A2, we just have like equals. So right here we'd have equals, and then we'd have the name of our macro, whatever that is. So it's a function we can execute in a spreadsheet program. And this is, again, a really simple example, but that's basically how it works. Now in the IB exam, it doesn't exactly work that way for God knows what reason. Basically what it is just an expression that you write to fill in a certain cell. So there's no reason to even really call it a macro, I guess, but it is what it is. So we have some expression like filled in right here, A1, and that would just be equals and then something based on other cells. So what we need to decide now is how we can use the information we have in other cells in order to calculate what the number of games is that in which, for example, team 1, team 2, team 3, and team 4 would have achieved a tie. So let's start with writing the macro for team 1. So if you look at this chart right here, we know that each of these right here is the number of games that team 1 has won, or is expected to win. And this as well, even though it's 0. So if we just think about if we're just going to think about team 1, and we'll just start with that right here. So team 1 is expected to win whatever is in B1 plus C1 plus D1. However, right here, so if we look at this right here, using a different color, these are all the games that other teams are expected to win against team 1. So basically all the games that team 1 is going to lose. So we'll say, I'm just going to call this win, and then lose. I'm just going to make some space here. So all of the teams, all the number of times that team 1 is going to lose is going to be whatever is in A2 plus B3, or sorry, that's going to be, okay, right here. So you get A2 plus A3 plus A4. So if we wanted to get the number of teams that ties, then what we would have to do is we would have to subtract, or we'd have to add up win and lose. And we know that each team plays every other team 10 times. So that means that Team 10 would have had to play 30 games. So if we take the number of times, or the number of games that Team 1 won, and add them to the number of games that Team 1 lost, that's the total number of games that are not ties. And if we subtract that, so if you subtract that from 30, we'll get the number of games that were tied. Whatever is left when we add up won and lost games and subtract that from 30 is going to be what's tied. So basically our answer for our first macro that we'd have to write would be A1 equals, and we could either use this notation right here with pluses, or we could say is 30 minus sum of B1, C1, and D1 plus sum of A2, A3, and A4. And that would basically be our answer. And again, that sum function is something that's available in any spreadsheet program. However, we could just use the simple addition sign as well, and that would work. All right, that's D1 right there. And basically we would do this for every single different spot or cell. So for B2, we would simply have 30 minus sum of, what's that going to be? Like, yeah, that's going to be A2, let's see, C2, and, okay, D2, plus sum of all the games that have been lost. So it's going to be, let's see, B1, B3, and B4. And that would be the answer for that one. And we would have to do that for C3 right here, and then D4 right here. And that's basically the way that we would solve our problems. And each one of these would be considered a macro. So this whole thing would be considered a macro. I mean, again, really, we're not actually writing the macro itself, but that's kind of how it works in the IB exam, I guess. So if you look at our mark scheme right here, it says add a team's wins and losses, subtract from 30, insert in correct diagonal, and that's basically what we did right here. Both examples cover the first two, okay, so whatever. So basically just going to do that, do whatever was right here and repeat it for other teams. And here it's just kind of a different way it's not a different way that's been done, but there's just different labeling that's been given. So I guess it says M1, M2, M3, and M4 for macros. But again, just using the actual cell where it's supposed to be inserted works perfectly fine as well. Now, actually what I wanted to do is actually just show you the next part of this question. We're not actually going to solve this, but it'll just give you kind of an idea of what's coming next. So it says during the year, the results of each game are used to complete a separate table, played. For each team, played stores the number of games lost, won, and drawn against each other team in a format similar to Prop 10. So Prop 10 is this one that we saw right here. After each game, information including the team numbers and scores is sent in the form I, J, M, and N. For example, 2, 3, 6, 1 indicates that Team 2 scored 6 and Team 3 scored 1. Using the data I, J, M, and N, construct an algorithm to insert the correct data into the table played. You can assume that the table contains 0 values at the beginning of the year. So it says construct an algorithm. And you've seen this phrase before on paper 1. Hence, we're actually going to have to go ahead and construct an algorithm. And we're going to write this algorithm. This is actually in the form of a macro because of the fact that if you looked here, well, okay. I would say it's in the form of a macro because we're actually referring to cells here. So we have some sort of table played, spreadsheet table, I guess, played, and we're actually inserting stuff into coordinates in played in like this sort of format, which I guess is really like similar to a 2D array format, but whatever. Anyways, we're not going to actually solve this right now, but our next section, after we finish this one up, is going to encompass just purely pseudocode problems because there is usually at least one pseudocode problem on every paper. Okay, so for our next problem, before we move on to pseudocode, we're going to look at this right here. And this is another spreadsheet-based problem. It says the population of rare tropical insects on an island follows a geometric model such that the population multiplies by k from one month to the next. So for example, if k equals 2, the population would double each month. The situation can be expressed as either this or this. So P of O is going to be the initial population, k is a constant, and Pn is the population after n months. So for a value of k equals 3, and initial population of 100, calculate the population after 2 months. So assuming we use this formula, we have n equals 2, right? And we have PO equals 100. So we could simply do P2 is going to be equal to 100 times k, which is 3, squared. So P2 would just be equal to 900. And on the other hand, if we wanted to use this formula, we could just do, okay, so I guess actually this formula would be a little bit different. We could use this to find the next value. So if we have P2 already and we wanted to find P3, we could just say P3 equals k, which is 3, times P of n, or P2. And that's 900, and that's going to give us 2700. So we can use either of them, but I think there's actually different use cases. So, okay, so now with the aid of a diagram, outline the way in which the spreadsheet could be used to estimate the size of the population after each of the first 10 months. So it says each, so that kind of assumes that we're going to have at least 10 rows of data where we're going to be doing some calculations. Really 10 rows of output. So anyways, let's go ahead and look at the solution and how that works. So right here, we have our spreadsheet, and we have one column with time periods and one column with population. And this whole thing, this whole mess right here, I don't really know what that's there for, but in reality, this is going to be cell 1, 2, 3, 4, because that's how it works in Excel. Now, I think probably the easiest way to approach this is to use this formula, where Pn plus 1 equals P0 times k. Just because like that is taking the previous, or not P0, but Pn, because this is taking the previous value into account, and that's something that's really easy to like write into a spreadsheet. So if we start right here with where the time period is 0 with the initial value, this is just going to be P0, right? It's going to be 100, and that's going to be at cell B1. So we can just say B1 is equal to P0. Or rather, I guess this is going to be B2 is equal to P0, because that's row 2. So B2 equals P0. Now to get this, we are basically going to say P1, we're calculating P1 equals P0 times 3. If you put that in terms of like the spreadsheet, then we can just say B3 is going to end up being equal to, it's going to be equal to whatever B2 was, times 3. And that's where we get this mess right here. So that's really what we'd fill in. Well, it's not a mess, but you know what I mean. And we'd keep doing that until we get to our 10th month, which is right here. And you don't necessarily have to write all of it out, but I would recommend actually writing the whole thing out, because this is just a solution, and just to be completely on the safe side, write everything out. Right here it says accept B2 times 2 to the power of A3, with A3 being the particular time period right here. Which actually, what this does do is disprove my previous statement that you can't use exponents. In fact, I think that probably anything you could use in Excel, you could use here. But I don't know, just in my opinion, this is easier and less ambiguous, just using this formula. But it doesn't really matter. Either way, you would get the right answer. Now, just as sort of an additional question involving spreadsheets. So right here it says, each month it is estimated that only 40% of insects survive due to various circumstances, such as climate and nutrition. This is known as a constant survival rate. Outline how this factor could be built into your spreadsheet, stating any assumptions that you make. Basically what that means is that at each time period, you would apply 0.4, right? So right here, it says basically at each time period, whatever your result is, you probably just, like for example right here, you probably just multiply that by 0.4, and then that would just be used as the input for your next value. So not too complicated, but this is just an example of a question that may come up, again, involving spreadsheets. Now, before we close up the spreadsheet section, what I do want to do is go through a little cheat sheet. So right here, I have the formulas for if statements. We already went through this in detail, but I still wanted to leave this right here to at least give you some examples for how things work. And then also for the sum function, which we saw in another bit of pseudocode. Now, there are two different ways you could do sums. One of them is actually the Excel way, which is actually this one with commas, and the other one is what I saw in pseudocode. But either of them should be valid in an option B solution. Now, one of the problems is that there wasn't really like a clear list on like what functionality you could use in pseudocode and what you can't, because in fact in Excel there is a lot of complex functionality that would basically make a lot of the questions, or yeah, basically make the question redundant. Like you could do a lot of the solution just using certain functions. So I know for a fact that you can use these on the exam, but anything else you can use, I'm not really sure, to be honest. And I would wager that most solutions or most problems are really going to require you to do things like sums or basic arithmetic, besides the if statement. Anyways, let's move on. Now this brings us to our section on pseudocode problems. Now we're going to go over about 3 pseudocode examples, and there's going to be some others in the slides that you can take a look at later. But just be aware that these questions are not very well written, and this is going to be probably the biggest challenge of the Option B exam. Anyways, let's get started. Okay, let's get started with our first pseudocode problem, which should be pretty familiar. So we saw this problem when we were doing spreadsheet modeling, and this is a formula for compound interest. Now T is our total value of an investment after interest. P is the amount of money we're starting out with, R is the interest rate, and N is the number of time periods for which we're calculating the total value of our investment. Now, if you look at our pseudocode question right here, it says each month is calculated on the monthly profit at a rate of 25% when the investment total is $40,000 or below. However, when the investment total is above $40,000, the tax rate is 40%. So we can pretty much say that when our total value is less than or equal to 40,000, that means that's going to lead us to a tax rate of 25%. And when it's greater than 40,000, then that's going to lead us to a tax rate of 40%. And this is being calculated on the monthly profit. So the tax is calculated at the end of each month after interest has been added. A running total of the tax is kept and only deducted from the investment total at the end of the year. So I think one thing to point out is that we're going to, in order to calculate tax, we'd have to go through every single month and then get the tax on the profit for each one of those months. But we're not going to deduct it until we get to the end of our calculation at the end of the year. Now, what I want to do in order to illustrate how we're going to, well, actually first let's just take a look at the problem. It says construct an algorithm to calculate the fund value at the end of each month. This algorithm should also calculate the total value of the investment after the tax has been deducted after 12 months. So in many ways, this resembles the spreadsheet problem that we looked at initially. And in fact, in order to write this algorithm, we need to use some information from part B of this problem. Part B actually precedes this problem, and it contains some information like the amount of money we're starting out with, the amount of money that's being added each month, and the interest rate. I can just go ahead and take note of that right here. So we're starting with 30,000. Our interest rate is going to be or we can actually just say 0.005 because it's 0.5%. And we're just adding $1,000 each month. And it doesn't actually say like exactly what the profit is, which is probably one of the downsides of this problem. But I would assume that our profit is going to be our interest and that $1,000. Anyways, if you go to our spreadsheet right here, we can observe that, basically in the spreadsheet, we did this calculation, but without the tax. What we did is we started out with our total, our principal. We multiplied it by 0.005 to get our interest. And we also kept track of 1,000 right here. And we basically added them all together. So right here, we had 30,000. Right here, we had the interest. And then right here, we had the principal. So our principal plus the interest plus $1,000. And then that value came right here. And then we got the interest on that resultant value. And then once we got the interest and added that to our result, our E2, then we added 1,000 on top of that. So first calculate interest, add it to our value for that month, add 1,000, and then use that value for the next month. We're basically going to be following this procedure for when we're writing our algorithm to calculate our tax off the profit for each month. Now, to calculate the profit, what I would probably say is that we would have to take, we'd basically have to take our resultant value, so whatever this is, and then multiply the $1,000 and the interest. And then so we probably just have like this part. So our interest, so we probably just have interest. So we could say like C2 plus D2, and then we calculate the tax off of this, and we keep track of that. So this would technically just like be our profit for each month. Now what we're going to do is we're going to go ahead and take a look at the algorithm. Instead of actually writing out the algorithm like I normally would, I'm actually just going to go through the mark scheme because it's faster, and also I feel like there's some things that happen on the mark scheme that aren't always clear, so it gives me a chance to explain any weird syntax that you see. Now let's take a look at the actual pseudocode solution. So the first thing we've done right here is actually create an array and initialize it. So this array is starting at index 0 and ending at index 12. So that means the first element is going to be P0 and the last element is going to be P12. And all of these are going to be set to 0, at least to start out with. What we're doing first is we're setting P0 equal to 30,000, which is just our like starting value. And we're calculating interest rate, which is 1.005, presumably so we can multiply it by whatever value we have for the month, whatever our principal is for the month, to get the resultant total with interest. And we're setting our tax equal to 0. Now that tax, this variable is going to be what allows us to keep track of the tax, the running total of tax for each month. So at the end, we can subtract it from our total investment value. So we have a loop running from 0 to 11, and inside that loop, the first thing we're going to do is calculate our value after tax, after interest. And what I'm going to do is I'm kind of going to trace this a little bit. So we're going to start with our first value, P0, and so that basically means that we'd have investment is equal to P0 or 30,000. Times 1.005, and the result is that we're going to get our we're basically going to get a value that includes both our initial investment and the additional interest, so our value after interest. And we're going to store that in P1. So right here we have P x plus 1, so that means P1 would basically be equal to our value after interest plus our 1,000. So it'd be like 30,000 times 1.005 or 1.005 plus 1,000. So if we go back to our table right here, it's basically going to be this calculation right here, like what we have, which I've circled like 5 billion times right here. So once we've done that, we're actually going to calculate the profit. As I said, the profit is going to be our interest plus 1,000. So let's see. Okay, we have 1,000 plus investment. Now, okay, so that means that our investment would basically be this value. So we're going to take this. That's interesting. We're going to take this and we're going to subtract P of X from it. So actually we're not even taking this part into account, which is something I didn't really anticipate. And to be honest, like, I don't really see anywhere it was mentioned right here. Like, okay, there's like profit isn't defined anywhere really. It just says it's calculated on the monthly profit, and I guess that profit is purely based on interest. So anyways, that's something interesting that honestly like wasn't even really mentioned in the problem. Anyways, so basically our profit is going to be our interest. It's going to be our interest. So if investment is P of X, it's our initial value times our interest rate. We're just going to take whatever our interest is, whatever the resulting value of our interest is, which is really in this case just P of O times 0.005, and that's going to become our profit right here. And then what we're going to do is we're going to check whether our total value, so P of X plus 1, which is all of this right here, and I should have done plus 1,000. So we're going to check whether all of this right here is going to be less than or greater than 40,000. And then based on that, we're going to apply a tax rate to this profit right here, this interest right here. So the profit, like the tax is being applied to the profit, and the profit is only based on the interest rate, but our interest rate is based on not only our value after profit, but with the additional $1,000 that we talked about before. And so we're actually basically going to do that for every single month. Again, we're just basically replicating what is in this table right here. And I'm not going to go through and trace everything, but we're basically going through this process, then going back up. We're doing it all the way until we get to index 11 so that we can calculate our value, our total value for the last month, which is going to be stored at P12. And keep in mind, whatever tax we have, we've been using these statements right here, tax equals tax plus something, to keep a running total of what our tax is. So each month we're adding it to this tax variable. We're cumulatively adding it to this tax variable we created right up here. And then at the end, we're subtracting that from our total investment total, or from our investment total. And that's basically how this question works. I'm not gonna lie, like it was not that clear. Like exactly what profit is was really not clear, but it is what it is. And we would have 1 point for creating our initializing our variables, another for setting our interest rate, calculating interest, which I believe would have been right here, add interest to 1,000 each month, if statement to determine correct tax rate, and output investment minus tax. Like probably if you mess this up, like with the with calculating the profit, I imagine you probably would have just lost like 1 point. I don't think it'd be a big deal, but still, like it's just not that cool. Anyways, that's our first pseudocode problem. Let's move on. So now let's take a look at our next question. So again, this should be a familiar one. We saw this scenario from the spreadsheet modeling section. EnviroBuild is a construction company that recently purchased land. It has permission to build either small houses or large houses, but not both types of houses. The maximum number of small houses that can be built is 10, and the maximum number of large houses that can be built is 5. We've got 3 variables. One is the house type, the number of houses to be built, and the profit, which is total sales revenue minus land costs, labor costs, and material costs. Now, if we look at our pseudocode problem, the following steps are used to calculate the total profit. We read the profit variable and the number of days variable from the spreadsheet model in B, which you can go ahead and look back to that if you want to, but we just need to read the variables from there. So it's going to be profit and just number of days, with number of days referring to how much time it takes to build a project, or how much time it takes to build a house. So we're going to calculate the number of months that the project will take, and that can be done based on the number of days. The rate of interest on the bank loan of $400,000 is 1% per month, and the land tax is $500 per month. So construct the pseudocode that will calculate the profit after these additional costs have been considered. You can introduce any variables if necessary. So we need to calculate the profit after. Well, first of all, I mean, basically we need to take the number of days and turn it into a certain number of months that it's going to take to carry out this project. Then based on those months, we can calculate what the interest is on the bank loan. And then we can also calculate the tax for that number of months. And we can subtract that all from the profit. So let's see how that's done in pseudocode. We're going to look at an example right here. And here we've actually just done import file CSV to get the variables we want. So we did import file CSV as SS, and we're going to have this read keyword for profit and number of days from SS, which is right here. Now, you've never seen this before, but this is something you can do, I guess, in option B. Now, the end date is going to be just a date. So January 1st, 2021, plus the number of days that we got from our spreadsheet. So the number of days it took to build a particular house. Now, it never actually tells us we're starting on January 1st, 2021, but I don't think it really even matters. This just gives us, and this will help us get an even number of months. So next we're going to do num months, and this is going to be month and then end date. So this month function is basically going to take the end date from the beginning of the year until this end date right here, and it's going to give us a number of months. So what's important to consider is that right here we have this hashtag, and it's actually done a different way in this other example. But we have a hashtag that makes that a date, and we add a number of dates. Our result is going to be the date data type. So end date is actually just going to be another date that looks like this right here. Now, number of months is you're going to get number of months by using a month function right here that we haven't ever heard of before. And then we're going to put our end date in there. And then that's going to tell us the number of months from the beginning of the year until this end date. So we get the number of months. And then we can calculate the costs. So number of months times 500, and this 500 is just the tax. And the number of months times 400,000 times 0.1. So actually, this is kind of weird. So let's go back and see what they told us about the actual loan. So it says the rate of interest on the bank loan is of $400,000 is 1% per month. Okay, so we're basically taking 400,000 and we're multiplying it by 0.01. And that's going to tell us the amount of interest we have for a given month. So interest per month. And we're going to multiply that by the number of months. So this part right here, we already have our tax for all of the months. And then we have our interest for all of the months right here. And then we're just going to subtract that from the profit, which is something else we got from our spreadsheet as well. Now, I just want to look at this other alternative pseudocode, just kind of see how things work. Now we have input profit num days from spreadsheet, and spreadsheet just represents the spreadsheet that we're getting these variables from. End date equals date eval, like the first date of the year plus number of days. So this is basically just giving us the date that is this date right here, plus whatever number of days we have that it took for that house to be built. And we use a month function again to get the number of months that are that end date represents from the beginning of the year. So you do kind of need to know how to evaluate this, and I'll add that in the section at the end with some like handy functions you can use. And so then our interest is going to be 400,000 times 0.01 times months taken. And I don't actually see where the tax was here, which is strange. There's no tax in this solution. We just have a profit calculation. So actually this was like actually ridiculous. This would not have, I can't see where this would have given us a correct answer. I could be wrong. This one I think would be a correct answer. But I just wanted to show you the syntax for dates again, which I'm pretty sure comes from Excel. And yeah, so that's how basically the pseudocode you write to solve this problem. Now I'd like to look at one more pseudocode question to kind of finish this section off. There are obviously going to be other pseudocode questions in this slideshow, but to kind of keep this a bit shorter and to prevent redundancy, I'm just going to solve one more question. So the rise in global temperatures has led to the melting of the sea ice in polar regions. Scientists have developed a number of computer models that can be used to make predictions about the rate of sea ice melting in these polar regions and its effects on coastal areas globally. In order to create a computer model, a number of variables have been identified. So the average ocean surface temperature, the albedo of the ocean, so the proportion of light reflected from the ocean surface, precipitation, and salinity of ocean, and area of sea ice. So now we're going to get to our pseudocode question. In this model, the following rules have been determined. For every 1.01 degree Celsius increase in ocean surface temperature, the area of sea ice decreases by 1%. So 0.01 degrees Celsius leads to a 1% decrease in sea ice. For every 1% decrease in the area of sea ice, the sea level rises by 20 meters. So I'm just going to write up, up, down. And then we can say for every 1% decrease in sea ice, the sea level rises by 20 meters. So down, up, and that's kind of our relationship there. And the initial values of sea ice or the area of sea ice are 1 million kilometers squared. The average surface temperature is 0.00 degrees Celsius. Using the rules and initial values above, construct the pseudocode that would enable the area of the sea ice and sea level rise to be calculated if there is an increase of 0.04 degrees Celsius in the ocean surface temperature. So let's go take a look at the pseudocode that was used to answer this question. So now let's go write our pseudocode solution. And yeah, one thing I do want to make sure that you understand is that basically right here we have a bunch of relationships. 0.01 degrees up means 1% down. So 0.01 degrees up in ocean surface temperature means 1% down in the area of sea ice. So we're going to start with an original sea ice temperature of 1 million and a surface temperature change of 0.04. And we want to calculate the new sea ice area. So surface area temperature goes up by 0.04. That means the area of the sea ice is going to decrease by 4%. So if it's decreasing by 4%, we can just multiply the original sea ice area by 0.96 basically. That's why we're going to have 1 minus the surface temp change, which in this case is 1 minus 0.04 and 0.96. If we multiply the original sea ice area by 0.96, then we'll get our new sea ice area. Now to get our sea level change, then we're going to have to take our new ice area minus our original sea ice area, and then divide it by this right here. So the sea level change is going to be based on the decrease in the area of the sea ice, right? So this right here, this expression right here is how much it's been decreased. And we know that for every 1% decrease in the area of the sea ice, the sea level rises by 20 millimeters. So what we need to do is we need to get the percentage of this change relative to the original sea ice. So really that new sea ice area, I'm just going to go ahead and erase this just so there aren't a bunch of like circles here. But so basically if we have like new sea ice area minus original sea ice area, so the difference divided by the original sea ice area, that's going to give us the percentage change, right? So that's going to tell us how many percent of a change. It's going to give us a decimal actually. So it's going to give us point something. Maybe we could say, for example, 0.5. And what we actually want to end up with is, so construct like the pseudocode that would enable the area of the sea ice to be calculated if there's an increase. So we want to get the area of the sea ice that's going to be left over, and then the sea rise. We already got the area of the sea rise, so now we just want to calculate the sea level rise that will take place. So for every 1% decrease, the sea level rises by 20 millimeters. So right here we have a decimal for the change in sea ice. But we want to find what percentage that is, which is why we multiply by 100. So we get our percentage, let's say that that's just 5%, and then we can multiply it by 20 to get our final sea level change. That's 20 millimeters. So for example, in this case, we would have, okay, what is 5% of 20? We'd have just like 1 millimeter. Now this is an example. We didn't really have to output it or print anything out, but that's just an example of taking our model and then just turning it into some pseudocode. So now let's take a look at some, like kind of like a cheat sheet for the different functions that you can use when you're writing pseudocode solutions. Now to wrap up the pseudocode section, I wanted to go over a few snippets that we saw in these previous practice problems. And these are probably some of the more unique snippets that I've seen from looking at all the practice problems. And the first snippet is basically importing from a file and then reading specific variables from that file. So basically, you're not going to be asked to actually even input a specific file name, but in the pseudocode, they just wrote file.csv to show that this information is coming from a CSV file. We named the data from that file SS, and then we read specific variables that were actually specified in the question from that file. Now, the next snippet involved dates. And here we created a date. We could say a date object in the context of programming. And we created it for the first day of the year. Then we added some number of days to it. And we took the result and basically turned it into a date again. And we ended up with a date object. And basically that date, when we took that date object and we applied the month function right here, we ended up with some number of months for this number of days right here. And this is basically the equivalent code. This basically does the same thing. This little pound sign right here basically again turns it into a date. We add numbers, we get another date object, and we calculate the months from that. I just wanted to go over those because those are kind of unique, and I hadn't really seen those before. But I do think that all the other pseudocode I've seen does not include any more exotic snippets like this. Now, one thing I did want to show you is in some of the older examples, rather than writing pseudocode in the traditional pseudocode syntax, there's literally just a textual explanation, which I believe is actually valid. So this is something to keep in mind if you still have trouble with IB pseudocode. Now, one disclaimer I want to give you is that some of the pseudocode questions in option B are an absolute enigma. Honestly, this is probably one of the worst written exams I've ever seen. And there's no real standard for what can and can't be done in pseudocode. There's really no sort of parameters for what can and can't go in a pseudocode solution, which makes it really hard to write something accurate or to even know what would be an acceptable answer. So if you're still kind of on the fence about doing option B, it's just something to keep in mind. And additionally, I would say if you're looking at some of these past paper questions, you don't quite understand what's going on. That's probably because you're absolutely right. There's no idea, there's just not enough information. Anyways, that being said, let's move on to the next section on visualization. Visualization, according to the IB, is a graphical software technique that creates an image, diagram, or graph to communicate data. We can say that it makes complex information more accessible and understandable, and some of the visual elements that are used in visualization are charts, graphs, maps, and 3D images to communicate complex relationships, patterns, and trends in data. Now, we need visualization models because oftentimes it's easier to understand visual data than raw data. Imagine looking at a chart versus looking at a bunch of numbers on an Excel spreadsheet. We don't need to interpret figures because those figures are presented to us in physical form, and so we can save time. And we can easily see the importance of specific trends or patterns. Moreover, visualization has a greater emotional impact than raw data. Think about looking at the effectiveness of a weapon system on the battlefield and seeing a huge spike in, for example, the number of enemy soldiers it's killed on a graph, in place of seeing just numbers, right? So visualization can have a greater emotional impact by its ability to easily display specific trends or patterns that have an impact. Now, the first step of visualization we're going to look at is going to be 2D visualization. Now, this refers to the graphical representation of data on two-dimensional surfaces. And that means that generally only length and width are considered when displaying data. We're not looking at depth, which would be the third dimension. Now, common use cases are graphs, charts, diagrams, maps, and illustrations. Basically, we're going to be using 2D visualization in scenarios where we don't need a third dimension to give any additional useful information. Now, some use cases for 2D visualization are simply in 2D data. So think data with an X and Y coordinate, or that can be presented in an XY form. When we really want simplicity and clarity, because 2D visualizations are simpler and clearer than 3D visualizations, because when you're projecting something in a 3D space, certain data can be kind of obfuscated or not shown easily. Additionally, if we want to use statistical or standard graphs to present data, many times these are going to be 2D visualizations. Think bar charts, line graphs, pie charts, etc. And finally, using 2D visualizations is less demanding than 3D visualizations in terms of computational resources, so memory and processing power that is used. They're easier to create, faster to render, and more likely to be compatible with various software and devices that require advanced hardware like graphics cards, for example. Now, oftentimes, we can use 2D visualization in conjunction with data collection. So we can collect data and then present that in a 2D form. An example might be using GPS trackers or internet-enabled measurement devices. So maybe we're collecting data in a physical space, like on the ground, and then we want to show this on a 2D map. That can be an example of 2D visualization where data collection is going to come into play. Now, some reasons in which we might use data collection in conjunction with 2D visualizations are in areas where it may be inhospitable or dangerous for data collection by humans, area too large for data collection, an area that has poor visibility, or there may be changes in certain variables that humans cannot keep up with. And specifically, the reasons for this, when we're referring to this, would be data collection methods, would be electronic data collection methods, like GPS trackers, or internet-enabled measurement devices. So the idea in this scenario is we'd use these electronic devices, and they would give us data that we could very easily present on a map or in a 2D form. Overall, this is just a scenario in which we would use 2D visualization, but it's one that's appeared on the IB. Now here we have an IB question, which I'm not going to go fully through, but it's basically a question where we're going to track antelope migration, and we're going to show it on a 2D map, and this is a great example of where and when we would use 2D visualization. In this example, we're also making use of tracking devices. Now the next type of visualization is 3D visualization. So this is when we're basically creating graphical content to represent 3 dimensions of data, and on the graph it would be length, width, and depth. So we may use 3D visualizations to depict spatial relationships and structures. So for example, if we want to show something like a building, or we want to show a 3D object, that's going to require 3D visualizations to see really the depth of something.
Maybe we might want to explore data that has 3 dimensions, and visualizing it in those 3 dimensions can make it easier for us to zoom in or look at specific aspects of those data in that 3rd dimension. Think about clouds, atmospheric layers, or multi-dimensional scaling and statistics. Next, we can often use 3D visualizations in simulation and training. So, for example, we might want to train people to respond to emergency situations. Other good examples are flight simulators, virtual reality medical training, or military exercises. These are great use cases for 3D visualizations because we're trying to basically replicate the real world. Now, here's a great example. It says vehicles are tested for their exhaust gas emissions using simulation software at specialist garages. During a period of 5 minutes, a vehicle with the engine switched on and is monitored for emissions of carbon dioxide and fine particulates. The software uses 3D visualization to display these parameters on a screen for the whole duration of the test. Explain how emissions of CO2 and fine particulates could be represented in 3D by the software. And if you look at the mark scheme, we can basically show the quantity and direction of the CO2, the diffusion of CO2, space of the CO2 moving outwards over the whole duration of a test. So we basically have quantity, direction, and those are 2 dimensions that we can show over time, which is our 3rd dimension. That's kind of shown here. X equals time, Y equals density of CO2, and Z equals temperature. Although here our 3rd dimension is temperature instead of something like direction. The point is we basically have 3 different variables that we want to show, and therefore 3D visualization is the answer in this case. Now next, in order to create 3D models, we need to do something called rendering. And rendering involves generating a 2D image from a 3D model so it can be determined or it can be shown on a screen. So the 3D model is really just going to be a bunch of coordinates that exist in our computer or are stored on memory. And we basically want to take this 3D representation, this mathematical representation, and turn it into a 2D image of a 3D object that can be shown on a monitor or some other display device. Now, some of the processes some of the steps in rendering 3D models involve first inputting details of a 3D object. So these are geometric coordinates, colors, lighting, texture, and orientation of a 3D object into a computer. Next, we want to deal with lighting. So we want to calculate how lighting interacts with the surface of the object. So how lit up is that object going to look like, and where is it going to look lit up? Next, we'd have to deal with texture. So we want to map characteristics such as glossiness, roughness, transparency, etc. onto the surface of a 3D object. And finally, we're going to execute the actual computational rendering, which is constructing 2D images to be displayed on a computer using a rendering algorithm, and data from the previous 3 steps up here. Finally, once we've done all of that, we can display our resultant image on our display device. Now, in order to handle the rendering process that we talked about here, we're going to need to use a rendering algorithm, of which there are 2 types we're going to learn about. First is Scanline rendering, and it's called Scanline rendering because, in a sense, we're taking our 3D scene with 3D objects that we have stored in memory, and we're kind of scanning it line by horizontal line. So basically what we're doing first is we're doing something called edge detection. We're identifying the edges of polygons or 3D objects and calculating where they intersect with the horizontal lines on the screen. And this helps us better identify their position in a 3D scene, so we can see where they should be displayed when they're viewed by the user. Now, an additional part of Scanline rendering is pixel processing. In pixel processing, we determine which pixels on each scanline are inside 3D objects and which are not. And we're going to calculate the colors of these pixels based on additional data on textures and lighting. Together, these compose of the Scanline rendering process. Now, Scanline rendering is quite efficient and optimized for real-time rendering because it focuses only on visible elements of a 3D visualization, so only those that are visible to the external user. This ability to effectively conduct real-time rendering makes Scanline rendering ideal for video games and interactive applications. Now, the next algorithm we're going to be talking about is going to be ray tracing. It's called ray tracing because basically when we use this algorithm, what it does is it emits simulated rays from a particular point in the 3D scene, known as the camera viewpoint. And based on where these rays hit, how they're reflected, etc., basically the algorithm maps out the entire 3D scene. Each ray checks for intersections with objects in the scene to determine visible surfaces, and then calculates precise details like shadows and reflections. The result is highly realistic images with complex lighting effects, and this makes ray tracing suitable for high-quality visualizations and animations, perhaps like those seen in films. Now, to compare these, ray tracing is generally going to be slower due to the computational intensity, and Scanline rendering is going to be faster, which makes it better for real-time rendering. Also, ray tracing has a higher demand on computational resources. Scanline is common in video games versus ray tracing is common in more high-quality uses. And ray tracing is great for complex lighting and reflections, while Scanline rendering is useful for more simple cases. So ray tracing, kind of emitting a sort of simulated ray of light from the camera's viewpoint. And Scanline rendering, basically splitting up the screen into horizontal lines and identifying which aspects or which edges of different 3D objects intersect with each of those horizontal lines, and then depicting 3D objects on the screen that way. So now let's take a look at an IB example or an IB problem that asks about the rendering process. Here it says a simulation software can be used to produce 3D visualizations of rising sea levels that change as the user alters the percentage of ice that is melted. In other words, real-time rendering. Once the 3D visualization has been rendered, when the user drags a slider bar to simulate the amount of ice that is melted, the visualization is re-rendered without any delay. Describe how this 3D visualization is rendered. Now this is a 6-point question, and right here the mark scheme shows some facts, not necessarily in order. Basically, we have a wireframe model that's created with polygons, 3D objects. We can say the 3D rendering process automatically converts a 3D wireframe model into 2D images in a computer. 2D images are combined to create a 3D image, which I think should be kind of obvious. It's likely that Scanline rendering is used because it uses less processing power than ray tracing. And it's unlikely that ray tracing would be used because of the time taken for rendering. This seems to be, as we said before, a case of real-time rendering. Now, wireframe images are basically like this. They represent a visual method to display the underlying skeletal structure of a 3D model, so basically in terms of lines. They illustrate the edges of models with points at the intersections where the edges meet, and these allow us to show the geometry of an object without other details like texture, color, or lighting effects, which are added later. Now, we use these to get a clear understanding of a structure, to understand how the geometric structure of the 3D model looks, and this can allow us to make changes to the structure before adding any additional details. These can be very efficient for design because working with wireframe images is much less demanding than an already textured and lit model, so a model with a skin, so to speak. It also makes troubleshooting easier. If we want to make sure a 3D visualization looks the way we want it to, if we strip down the model to its basic form, the skeleton, it can be easier to find any problems that may exist early in the development process. Finally, wireframe images are used as sort of a universal communication tool. We can easily look at a wireframe image regardless of the context and understand what it's depicting. So this actually just brings us to the advantages. So transitioning from the memory of the model to a screen representation is really fast. So going from a wireframe image to a screen representation can be a very quick process. We can make multiple changes with little processing. And if we were manipulating in the design stage with a solid model, that would take a lot more memory and be time consuming. Finally, we can rotate a wireframe model without having to use a lot of computational resources in order to see what's going on inside the model itself, so with some depth. Now, we store wireframe models in memory in a specific way. So we're going to store the lines. So each line is represented as a vector. So a vector having a set, just being a set of x, y, and z coordinates. So actually, just to clarify, the vector is going to be defined by the 3D coordinates of its two endpoints. So the beginning and the end, which are going to be x, y, z coordinates. We apply mathematical handling, so algorithms are used to determine the interactions between lines, such as identifying where lines cross or touch each other. So you may have some data attached to the vectors, or actually we can just use the vectors to figure out where there are intersections, and where they're touching each other, because this is ultimately going to dictate the shape that's going to be produced by wireframe images. These are essential for rendering the resultant image on a screen correctly. Also, attach different vectors or different lines. We're going to have things like thickness, color, or style. And finally, algorithms are going to determine which parts of the wireframe are hidden or visible from a given viewpoint. So we can take these wireframes and use algorithms to determine what's going to be shown and what's going to be visual, which is going to be useful when you get to the rendering process. Now, sometimes we might have to dynamically re-render a 3D model, and wireframe models can be useful for this. So basically we can take the existing 3D visualization, convert it to we're going to convert it to a 2D image. But these 2D images can be easily updated and converted back into 3D images. Actually, let me just go over that process again. So let's say we want to re-render something in real time, which this is probably going to use actually Scanline rendering. So we can take the existing 3D visualization, it's created with lines. We can convert it to 2D images. We can update these 2D images, and then we're going to convert them back to 3D images and add any photorealistic effects. And these 3D images are then going to be displayed on our screen. So basically, using wireframes, we are going to take that wireframe, we can turn it to 2D, update the 2D, and then convert back to 3D. And this is not something that this is something that's going to be done automatically by a computer program, and it's going to use Scanline rendering. And once we convert it back to 3D again, after making the changes in 2D images, we can add any effects. And there's going to be probably a rendering process that's going to be used again to actually get it displayed on the computer screen. Now, some of the challenges of 3D rendering include the fact that rendering individual frames can take time, from a few seconds to days, depending on how complex the screen is. And rendering for non-interactive media, such as animations, is much slower than for interactive media. And generally, it's going to be of higher quality. Generally, 3D rendering is very computationally intensive, requiring a lot of memory and processing power. It brings us to some of the requirements for 3D visualizations, which are a powerful CPU, a high-performance GPU or graphical processing unit, and adequate RAM. From a software perspective, we're generally going to need 3D modeling software and dedicated rendering software to carry out the rendering process and enhance the quality of the final output with lighting and shading options. And that software can be expensive as well. Now, the next type of software we're actually going to talk about is going to be CAD software, computer-aided design. And this is used extensively to create detailed 2D and 3D models of physical components, which allow us to visualize how objects will look and feel. These are particularly used in technical professions such as engineering, architecture, and design. These are different from normal software that's used for 3D visualization because they offer very high precision in designing complex components. They ensure that components fit together perfectly and operate as intended. And they can also support things like simulation and analysis, which can allow us to evaluate the performance of design before it's manufactured. So again, this is geared more towards manufacturing. Now, this is an example of CAD software, which is being used to simulate a bunch of components and show how they fit together. Now, some of the advantages of CAD process and the design process include the fact that we can construct an initial wireframe, and this can be rotated and viewed from any angle. So we can basically analyze the model we've created from multiple perspectives. It can be very quick to revise. So changes to design can be made quickly in CAD, and we can immediately see the effect on a 3D shape. And this is actually kind of related to the previous point. It's very simple to undo changes in CAD software and erase parts of a sketch. So it can be much more flexible in terms of making changes to designs. Actually, to rephrase that, we don't need to erase parts of a sketch, but we can quickly and efficiently just make changes in our CAD software that don't require that. Finally, scaling is quite easy in CAD software. We can make designs bigger or smaller, so we can scale designs up or down in a precise way. And finally, all these designs in our CAD software are digital, so they're less prone to damage or loss compared to physical drawings. So it's much more efficient to use a digital tool like CAD software than to try to draw wireframes and design in this way. So generally in the design process, we can say CAD software is much more efficient than just drawing things and eventually hoping to turn them into a 3D object or whatnot. Now, when we want to compare whether to use 2D or 3D visualization, there are a few factors to take into consideration. First, the objective. So we want to use 3D visualization for complex spatial data sets, but we can use 2D for simpler data sets where we don't have an additional dimension. Audience engagement is another factor. So if you have interactive experiences, 3D can be more beneficial than 2D. But if we just want to have more easily accessible, straightforward visuals, then 2D might be better. Technical resources is another factor because 3D takes up more hardware, software, and personnel resources than 2D. Finally, performance. So 2D can be more quick loading and can allow for real-time interactions more easily, versus 3D can allow for more dynamic interactions, but it could be slow and sluggish depending on the hardware being used. Now, before we close out this section and really the SL section as a whole, I'd like to take a look at two practice questions that I think will enhance your understanding of 2D and 3D visualization. Right here, an old set of 2D animated cartoons from the 1940s has been discovered and it is decided to modify them to turn them into 3D animation. Outline the need for rendering and the creation of the animated 3D characters, and then explain two technical implications of implementing a 3D animation this way. Let's take a look at the mark scheme. So first, outline the need for rendering and the creation of the animated 3D characters. Basically what we're doing is we're kind of talking about why we need rendering to take the 2D cartoons and turn them into 3D animations. Now, the characters are defined as mathematical models. They will need rendering to give a 3D effect. So right now they're just like 2D images and they're just mathematically defined, but we need to render them to actually take those 2D images that are stored and allow them to be depicted as 3D objects. That's what rendering does. Every movement will need to be fluid. The animation is less interesting with flat figures. So really, this is just telling us that we want it to be 3D, because otherwise it wouldn't be as interesting if it was a 2D animation. And in order for each movement to be fluid, especially in 3D, we need to use rendering to calculate where different aspects or different physical components of the animated figures would go. And we can't really do that without rendering. I think the fact that they're defined as mathematical models is just something that would make it easier for rendering. And the next question was telling us what are the implications of implementing a 3D animation this way. There's actually quite a lot of them. So rendering for non-interactive media such as animation is a slower process. Rendering time for individual frames may vary from a few seconds to days depending on the complexity of the scene. Rendered frames are stored to a hard disk and then transferred to other media for playback. These are all kind of just different facts talking about rendering, which I think are still useful to go over. 3D rendering is computationally resource hungry. So while computer processing power has increased greatly over the years, enough computational power still can't cope with the growing demand of realistic 3D animation. And weirdly, this is actually like kind of referring to like what is going on with 3D animation in general. It says implementing 3D animation this way, but what it's really talking about is what are the consequences of trying to use 3D animation, which is kind of weird as far as the question goes, but it still presents some good information as far as understanding what 3D rendering and animation is and what their implications are. Now, to look at the next question, this question actually focuses on wireframe models, and it's quite substantial, which is why I did want to go through it. Bridges are modeled, and these models are tested using sophisticated software before being presented for construction. The software enables the architect to define the shape of the bridge, apply parameters such as width, length, and material to the structure, view the bridge from different perspectives, and test the strength and stability of the bridge under all conditions. The architect starts by defining the basic shape of the required bridge, which includes the span of the bridge from one end to the other, struts or pillars that are needed to support the bridge. During this phase, the architect has a wireframe image to work with. When the design is complete, the image is rendered to give a solid view of the bridge. Outline the way in which the wireframe image can be used by the architect to adjust the parameters and view the bridge from many different perspectives. So basically this is asking why are wireframe images useful for someone who's doing construction work? The shape can be seen as a set of connecting lines. These represent the structure of the bridge and supports with corresponding variables. So it's more like a feature of using a wireframe model. We can use a library of predefined shapes that can be added to the design. Parameters can be changed to basically better analyze the design and how it would work. Parameters can be changed by entering values in cells or dragging vertices of the wireframe. And we can also rotate the wireframe so that all parts of the bridge can be seen. So they're basically things we already know about wireframe images, but it's still good to see them in a more practical context. Now describe how the wireframe image of the bridge is held in memory. I think this is actually pretty important. Let's take a look at how that is. So each vector representing an edge is basically held in memory as two 3D coordinates, with these coordinates being the endpoint. So basically you have 2 points that represent a vector, the beginning and ending. Mathematical formula are used to calculate where lines cross and touch to basically allow us to build a structure. And parameters such as thickness are linked to each line. We can also define hidden or visible parts from different views. Next question suggests reasons for making changes in the wireframe model rather than the solid view model. We already went through this, but I think it's not bad to go through it again. The transition from memory of the model into screen representation is fast. So basically we can take a wireframe model out of memory to the screen and see on the screen much more quickly. The architect can make multiple changes with less processing than in a solid view model. Because the solid model would need to be rendered each time, which is memory and time consuming. And if we want to rotate or analyze the wireframe to make changes, the processing in memory is minimal and is less than with a solid view. This is basically again comparing a wireframe model with a solid view model. Now suggest a strategy to test the model and ensure that the bridge will be safe once constructed. So this kind of goes back to, I guess this is really just more of a contextual example rather than giving us any new information about wireframes. But we can use the model and apply conditions such as higher than expected traffic, normal and maximum traffic and extreme weather conditions. And we can also measure the response to the structure in these conditions with regards to bending, etc. So we can basically apply different situations that place pressure on the structure. And then based on how that structure reacts, we can then change the bridge, which is quite easy to do with a wireframe model. Now this brings me to the end of this video. I wanted to include the HL section as well, but this actually turned out being pretty long at around 2 hours. So I'm just going to close it out right here. The next video to come out is going to be the option B HL video. I'm going to do a video comparing the paper 2 options, and I'm also going to come out with an HL pseudocode video, hopefully before the exams. And of course, long term, I'm always working on A-level videos. Anyways, thanks for watching this video. If you found value in it, please like and subscribe to the channel. Have a nice day.